Here we are once again, the physics video lecture. Physics 105B, video lecture 42. So we spent a lot of time just deriving the equations of motion for fluid mechanics. So now we have them, we actually want to do some applications. So we'll write down our equations just to have them here. The continuity equation, and now we have Euler's equation as well. Euler's equation, which is really just Newton's law applied to a droplet of water, and that's the left side. That was acceleration, and force was minus gradient of the pressure divided by the density. Yeah, so this is continuity once again, and this is Euler's equation. Okay, so our first example, and by the way, I'm going to explicitly include the acceleration due to an external field. That's what this is, and typically it doesn't have to be, but it's gravity in this case. And like I said, later on we can incorporate this into the definition of the pressure if need be, and then we have a more compact equation. We're going to use it in this form because that's our first task. So once again, Euler is to talk about hydrostatics. Next, hydrostatics. And in that case, there is no velocity, so the entire left side of this equation vanishes, okay, V and its derivatives. So hydrostatics, V identically equal to 0, and we're using the right side of Euler's equation. So what do we have? Gradient of P is equal to rho G. Okay, so now we go ahead and set up an orientation. Say we've got the Z-axis here. I'll just put a 0 there. Z-axis is up, G is pointing down. So in this case, this is up. So here, G is equal to minus G K hat, where that's our standard gravitational acceleration. And this differential equation is pretty basic. We have the P dx equals 0, dP dy equals 0, and dP dz, the z component of the gradient, is equal to minus rho G. So continuing right under here, that means P is equal to some constant minus rho G Z inward down. Okay, that's the famous pressure versus depth formula. So pressure versus depth, and the way you often encounter it is P equals P0 plus rho GH, where H is the depth, so measure positive direction. So if you have a water surface here, and you go ahead and call this 0, P0 is typically your atmospheric pressure, but remember, according to Pascal's principle, if you're somehow pressing down on it with some other force, then that would be your P0. Yeah, so you've got the atmospheric pressure, and you've got, say you've got some object down here, milk carton, some kind of box or something, and that'll take us to our next topic, the buoyancy force. Okay. We know this from experience. We have something submerged, it's less dense than water. We feel a force push down, it's pushing back at us, and that's the buoyancy force. So good, we've got our pressure depth formula. Although, there's actually one more thing to say about this. The pressure only depends on the depth, so in the z direction here. And it doesn't matter how large the volume of water is in the other dimensions. So for example, this is somewhat non-intuitive when you hear it for the first time. Suppose you had a dam holding back a large body of water. Okay, so here's a dam. There's the lake. We've got colors here. There's our, in fact, let's make the full depth for this guy. Okay, so there's a large body of water behind the dam. And who knows, you could have a hydropower plant or something. Be that as it may. The pressure at some point here, red star, pressure here has nothing to do with how far back this lake extends. It's really just a function of the depth, and it would be equally great if this water were terminated right here. Okay. So that has interesting applications that have been kind of played around with. For example, there's a famous one where there's a barrel full of water and just a long, long capillary. If that thing is long enough, extends high enough, then the pressure will be so enormous, despite the fact that it's a very small mass of water in the capillary. Nonetheless, the pressure will be enormous and burst the barrel. That's one you guys could look up. So that's just examples here. So just so we have some to write down examples of pressure only depends on the depth. The depth or the height of the column of water. Interesting topic right there. Good, so we've got that pressure versus depth formula. And the next thing we'll do, as I said, is the buoyancy force. So good, we can send this up. So, buoyancy force. And this time, here's our z-axis, here's our body of water, and we have some object in here of arbitrary shape, submerged object. Submerged object. So what do we have to know about this? The force is the force due to the pressure, so we can first start by just writing F is equal to minus the integral P, gradient P, rho gradient P d area, okay, surface area, and again the minus sign because the pressure is acting force due to the fluid is acting like that from all sides, whereas the surface normal is pointing out, so that's where you get the minus sign. So that's our vector. We're going to do the same thing we did earlier when we derived that. And I'm calling this F sub B for buoyancy. And I'm going to do the dot product again, just as we did before. So F sub B ith component would be equal to negative integral rho x I hat, and then we've got gradient. Oh, wait a minute. That was too soon. Yeah, that was too soon. Force is just pressure. What's more with feeling? Okay. Pressure times area. So we have to start with minus P d area. Gradient comes in later. So minus P d area, and this is the boundary of our volume V. That's the boundary of that. That's what that sign means. So we can also write this minus integral P n hat d area scalar. That's better. That's that outer surface normal. And now we're going to take the ith component of this vector, and we'll have minus integral same thing. So here's where we take that scalar product. So we have P x I hat, that's the unit vector, which gives us the component. N hat, that's the dot product. N hat, the area. And now we're going to use the divergence theorem. Divergence theorem, as we did before, minus integral volume divergence of P x I hat d volume. Okay. So then we use that same identity that I had assigned to you guys last time. So the divergence of this is going to be minus integral minus rho g from the pressure. Oh, we'll do two cases. Over the volume, E volume, if x of I hat is equal to k hat. Otherwise, right, we're using that function right up there. Otherwise, we get 0. 0, comma, if x of I hat equals I hat or j hat. Okay, so there's our expression. And again, we had using, this was last time, this was assigned to you guys, but divergence of a scalar times a vector is equal to P div that vector plus that vector dotted into gradient P. This is the one that vanishes, and this is the one that shows up right here. Okay. So this is the calculation, but we have to draw the conclusion. minus minus is plus, rho times g are constants, they come out. Integration over the volume is just the volume. So what do we have? We have for our buoyancy force that it's directed in the z direction. Okay. So there's our object that's directed in the positive z direction, and its magnitude is just given by, like I said, rho g are pulled out. I didn't state specifically, but I should have, that we were assuming rho is constant. Okay, so rho g are pulled out, and integral dv, v is just the volume. So that's rho times g times v. So that's the buoyancy force, and let's state it in the form of Archimedes' principle. So Archimedes' principle, first we'll just write this in the following way. The buoyancy force is equal to rho times v, I'll put parentheses around it, times g. Density times volume is mass. This is the density of the surrounding fluid. So density times volume is mass of the displaced fluid. Right? Density has nothing to do with the density of that object. Density of the surrounding fluid. So Archimedes' principle, buoyancy force is equal to the weight of the displaced fluid. So mass of the displaced fluid, and you multiply it by g, you get the weight. So Archimedes' principle, buoyancy force equals the weight of the displaced fluid. Last time I taught this to people, it turned out they didn't remember all of these basics. This or Bernoulli's equation, etc. So it's worth it. We'll just take the time. It's a really fundamental law. So we've got our buoyancy force, weight of the displaced fluid, mg, density times volume of the displaced fluid. So let's do a couple of examples. If you haven't seen this stuff for a while, it'll do you no harm. So the first example possibly goes back to Archimedes himself. Say you want to find the volume and therefore the density of some small, intricate object. Okay. It's difficult to find the volume because it's small, and if you try to displace a certain amount of water with it, the water line doesn't go up enough. Okay. So you're displacing some golden object here, and you want to know its volume. So find volume. So I can just label this now. This string here, let's see what we'll do. So what's acting on this little gold ring or something? Okay, what's acting on it? There's its weight. Now its weight we can get just by weighing it in air, no problem. Okay. There is a tension in the string, and that's a measurement as well. Here, I'll put some kind of identifier there. There's a tension in the string, and now there's also a buoyancy force. So F sub buoyancy, and what we get, here, let's do this right. We have, for the net force being 0, we have the tension plus buoyancy force minus mg equals 0. Right? We just add the buoyancy force to our other forces. And this is being measured. So you can say this is the weight in water. And of course this is the weight in air. More strictly in the vacuum, okay. And there's buoyancy force. So once again, let's go ahead and fill in. We have tension plus density, volume G minus mg, and we're just going to solve for the volume. And that's, again, like I said, the weight in air minus the weight in water divided by density of water times G. So that's a way to do a very fine volume measurement. Once you have the volume, of course, you can find the density. So this is the density of our fluid, which we're assuming is water in this case, but it doesn't matter. The density of our object is now going to be its mass divided by this volume that we just measured. So this is how you could determine the density of an object. Say, you want to know if it's lead, if it's gold, or if it's gold-plated lead. Okay, how are you going to do that? Well, you'll measure the density, and the density of gold is 19 times the density of water, and the density of lead is about 11 times. So it's a huge difference, and so don't ever be fooled by gold-plated lead. Okay, a little gold nugget that's actually lead will have roughly half the density of real gold. Good, you heard it here first. So that's a nice application, and I think it's the legendary application with which Archimedes was able to find the embezzler, or discover that someone had embezzled gold versus silver or something. Look it up. That's a good example. Let's see how we're doing time-wise. Yeah, we'll do another example just to make contact with these really elementary things. They're important. The other example is just lift of a helium balloon. That's also a buoyancy problem. Helium balloon. So we've got the balloon here. Okay. We've got a string on it or something. And once again, it's going to be the buoyancy force, but we have helium inside and air outside. So air is the fluid within which the helium balloon is floating, so to speak. So again, we would have mass of helium times G that's enclosed in the balloon. We would have the buoyancy force and mass of everything else, the actual balloon, the payload, etc. I'll just call it the mass of the payload, but that's everything else. So we want the balloon to float, and we have buoyancy force minus mass of helium times G minus mass of the load times G equals 0. We then have density of air, volume of the balloon G, Now the mass of the helium is the density of helium times the volume of the balloon times G. Okay. And I'll bring this to the other side. Mass of the load times G. And so you can see what we have here. G will cancel from both sides. We'll do that now. And we're looking at the difference in the density of air and helium times the volume. That's the mass of the load. So Archimedes' principle, the air is more dense than helium. This is about 1.2 kilograms per cubic meter. Is about 0.1 or 0.2. Look it up. So yeah, you're roughly getting 1 kilogram of load per cubic meter. And it's interesting, it's independent of the strength of your gravitational field, which you might not have guessed. Okay, so there you have it. Okay. So now we want to go back to a couple technical problems that we're going to wrap things up with, just to show you what's possible. Let's see how we're doing time-wise. Good. So this time we're using Euler's equation. And it's the rotating bucket. So a rotating fluid, imagine a cylinder of fluid that's rotating, and eventually it's rotating like a solid. When you're starting it up, all kinds of things are going on that are really complicated. But if you wait long enough, the water is rotating with the same velocity as the bucket. So it's in essence, it's like a solid. So next, rotating bucket. So there's our bucket. There's our z-axis. And it'll have rotation. Actually, I think I use a different letter. Yeah, I'm gonna use a capital omega. But first, let's start with Euler's equation again. This is an interesting one because just based on what I just said, we know the solution. So we're actually going to write down the solution and just see how everything balances out. Okay. So we start with Euler's equation. V dot grad V equals minus 1 over rho gradient P. And I'm going to put the G in explicitly. So yeah, the z is the up direction as before. And, our continuity equation, in the incompressible fluid case, we have divergence of v equals 0, and so that is a full set of equations. 1, 2, 3, 4 equations for velocity and pressure. Rho and g are constant. Okay, so this is the rotating bucket. And since it rotates as a solid, we're just going to take the fluid velocity as the velocity of that solid, of all the points in the solid. So here we have, we'll write this because the fluid rotates as a solid after it's gotten up to speed. Before it gets up to speed, you know, there would be slip between the, well, there would not be a uniform rotational speed at all. There would be slip and friction and everything else, and eventually it all comes together. But that's, and at that, for that initial phase, this equation wouldn't even be valid. But once it's rotating as a solid, it is valid. So what do we then have? We have V is just equal to the cross product of omega and the vector R, you know, in that fluid. So, you know, we have a XYZ coordinate system. Z is up, and that's what we're rotating around. So we've got omega cross R, and let's just write this out as 0, 0, omega crossed into XYZ, which are the components of the vector R. And this is something we know from rigid body motion, so that's what we're using here. And doing that cross product, we're going to obtain minus omega y, omega x, and 0, as has to be. And right, this is just standard expression for circular motion. Okay. So the velocity, of course, has no z component. Right? It would just be tangent for circular motion. There's a minus sign there. Out at xy. Okay. So good. We have that. So this is our vector, and what we're going to do is twofold. Make sure divergence of V vanishes. Note, divergence of V is equal to d dx dx, d dy dy, d dz dz. So when we plug that in, we're going to see it. Derivative with respect to x of this vanishes. The derivative with respect to y of this component vanishes. Right? So that's 0. Excellent. What about this thing here, though? Here's our chance to, you know, this is a great, unique situation. We were able to guess the solution, you know, of this monster operator here. And so yeah, we've taken care of that. Now, the explicit partial derivative with respect to time, of course, vanishes, right? There's no explicit time in there. So what we're really doing is checking this expression here. So I'll send it up. We'll check that. Next, check V dot grad V. So this, of course, is a vector, and we would have Vx d over dx plus Vy d over dy. That's this operator, no Vz, applied to Vx, and we would have the same thing. D over dy applied to Vy. So presumably we can just look at this thing and see what happens. Again, this is Vx, this is Vy, this is Vz. So Vx, d over dx times dx, that's 0. Vy, d over dy, so Vy is omega x. Wait a minute, what's more we're feeling? Vx, d over dx of Vx. Yeah, that was, the first one was 0. Vy, which is omega x, d over dy of Vx is minus omega. And then down here for v sub y, Vy d over dx of Vy, so we have, that's going to give us something, Vy d over dx, Vy, you get the same sign under it. Omega we consult for it. Ah, yes. We get minus omega squared x, and here we're going to get minus omega squared y. So why am I not seeing that? Dx d over dx. Okay, that one vanishes. I'm not seeing a sign here. Oh, because this is Vx omega. Omega squared y. Yeah. Still not seeing it. Bear with me. Omega. Oh no, that's good. Excellent. Okay, so we do have this fair and square. Now, we're looking at this equation. So apparently we have minus omega squared x equals minus 1 over rho dp dx plus g sub x is omega squared y e dy e sub y. So those are going to drop out, and we now have a differential equation for p with respect to x and p with respect to y. So remember, g only had a g sub z, so that's 0. But now we can integrate this. So what we get is dp dx equals rho omega squared x, got minus on both sides, e equals 1/2 rho omega squared x squared plus, remember these are partial derivatives, and in terms of y we get the same thing, p equals 1/2 rho omega squared y squared plus and so on. So what we're going to get now is a function for pressure altogether, and that looks like this. E equals going to factor this out, 1/2 rho omega squared x squared plus y squared, which we get from, we test it with the partial derivatives, but then we also have minus rho gz. And if we want, we can have another constant as well. So this is our pressure distribution. And what I'm going to do, this is a great place to drop this into your lap. Well, here's what I'll do. I'll finish it up. Let's make sure we get 1 minute or 2 left. Yeah, we're good. Okay, so we solved Euler's equation for the pressure because fortunately we knew what the velocity was. Okay, constructed it, found this, and we're able to now solve for the pressure. And the last thing we'll do is evaluate this at the surface. So here's our result. And I'm going to write, finally, evaluate at the surface. So at the surface of the fluid in that rotating bucket. And what we have is P naught equals, right, and I'll write atmosphere, imagine it's the atmosphere at the surface, 1/2 rho omega squared x squared plus y squared minus rho gz plus P atmosphere. So at the surface, we've got the atmospheric pressure, both places here, and what we're left with is z as a function of x and y. So z is equal to, and you can see now the g will be in there, the density will cancel, so we'll have omega squared over 2g x squared plus y squared. That means we have a paraboloid shape. So a rotating fluid takes on a paraboloid shape, which is really nice if it were, say, molten glass, and you wanted to create a large mirror for, say, an astronomical or for a telescope. Then you could rotate that glass while it's hot and fluid, keep it rotating, and then when it cools, it'll solidify into the appropriate paraboloid, which you can control by the angular frequency there. So paraboloid, which is a pretty nice result. By the way, you can get this by simpler means than Euler's equation, but we're talking about Euler's equation, so it's a great example. Let's see if we have anything else to say about this. I think that will do the trick. I have a couple of other topics on this, but we'll save that for next time. Yeah. Box around here. Good. Rotating bucket example. Okay, we'll see you next time.